All right. Hello, everyone, and welcome to Math with Miss Leslie. Yeah, I still haven't come up with a better name for our videos. This is the second to last video, so I'm not going to come up with one anytime soon. All right, here we go. So today we are going to do geometric sequences. This is actually day 3. I know it says day 2. I forgot to change the number. It's too late to go back now. So we're going to, same thing as with arithmetic sequences, we're going to define what it is to be geometric. We're going to look at the recursive equation, the explicit equation, and then we're going to do 2 examples, and that's it for today's video. So let's get going. There we go. Okay. So, like I said, first things first, we need to figure out what is a geometric sequence. This is a sequence where your terms to go from one to the next in your sequence, you are multiplying by the same number. So sorry, hold on, I gotta pause recording. All right, that's not that much better. I have like lotion on my hand, so holding the pen was like slippy. I tried to wipe it off. We'll see. I might just drop the pencil. It feels like that's what's gonna happen. Okay, so anyway, so geometric sequence is when we are multiplying by the same thing each time to go from one term to the next. So this is a sequence, where you multiply by the same number to get consecutive terms in a sequence. Consecutive terms in a sequence. All right, so that number that we're multiplying by, we call that the common ratio. All right, so number you multiply by is called the common ratio. And in our equations, you're going to see a lowercase r as the symbol for the common ratio. Just so when we were doing arithmetic, it was a common difference. And we use a lowercase d. In geometric sequences, it's a common ratio, not ratio, or a ratio, and we use r as our symbol. Okay, so for an example, right, so we want to do look at a quick example. We'll make it easy. 2, 4, 8, 16, 32, ... All right. So 2, 4, 8, 16, 32. So we are not adding the same number each time, right? 2 to 4, we're adding 2, but 4 to 8, we're adding 4. So what we're actually doing is we're multiplying each term by 2. So to go from here to here, we multiply by 2. Here to here, multiply by 2, so on and so forth. All right, so this 2 is our common ratio r. That's a geometric sequence. All right, so for recursive equation, you guys already know recursive is when you're using a previous term to get the future terms. We talked about last video, the Fibonacci sequence is one of those recursive equations. It's like the most famous one, right? And that's where you're adding the 2 previous terms to get the next term. But so recursive, you can do this with a geometric sequence also, and this is what your equation would look like. So a sub n equals a n minus 1 times r. So you're literally, this equation is just saying you're taking your last term and you multiply by r to get your future term, right? So a sub n is the term you want, a sub n minus 1 is the previous term, and like we just said, r is the common ratio. Cool. All right, for our example problem that we were doing up there, so the 2, 4, 6, 8, 2, 4, 8, 16, 32, this would be, so for our example, it would be a sub n equals a n minus 1 times the common ratio of r, which in our case is 2. All right, explicit equations. Let's zoom down a little bit there. Okay, so explicit, remember this is when you are using the term number to find the term that you want. So recursive is when you're using a previous term to find the next term. Explicit equations, these are when you are using the term number itself to find the value of that term in the sequence. All right, this is the equation that we generally use the most often because we don't really care about all the terms of a sequence. We generally are looking for a specific term. And in math, that's what's going to happen more often than not. Now, if you're looking at more applied mathematics, computer programming, recursive is actually going to be very beneficial, but we don't care about all the terms in between. We generally in math are going to be looking for specific terms. So generally we stick with the explicit equations when we are doing kind of like our math in this class specifically. And next year in calculus, you'll be using the explicit equation way more often than any recursive equation. All right, so to do an explicit equation for a geometric sequence, it looks something like this. So you still have that a sub n, all right, and then you're going to start with, you're going to take the first term, so a1, and you're going to multiply it by the common ratio to the power of n minus 1. So you now have this exponent in here. All right, so just going over what everything is. So a sub n again is the term you want. A1, this is the first term of the sequence. R is our common ratio. And then n is the term number that you want. So a sub n is the term itself, and then n is the term number in the sequence, right? So are you looking for the 50th term? Are you looking for the 12th term? That's n. So n is your term number. All right. So that is your explicit equation setup. So just like with recursive, we're going to use that example that we came up with in the beginning. So that 2, 4, 8, 16, 32, and we're going to make our explicit equation. So this would be a sub n equals, our first term in the sequence is 2 times our r value is 2 being raised to the power of n minus 1. And this is it. This is as far as you can go. You cannot combine the 2 and the n. Technically, you can because they are the same number, but it wouldn't just become like, some people say it's like 4 to the power of n minus 1, and that is incorrect. So something like this, you really would just leave it like this as is. Now, because this shares a base number, if you want to get fancy, if you are multiplying by something that has the same base, then you add the exponents, right? So if you have like x squared times x to the third, you would get x to the fifth. Well, this is the same kind of deal. So this 2 would be to the power of 1, all right? And then the other one is to the power of n minus 1. So if you want to be a little bit extra fancy, you could simplify this specifically because they have the same base number. And you would say that this is 2, and then you would add your exponents. 1 plus n minus 1. So this actually becomes 2 to the power of n because 1 minus 1 is 0. So that is your explicit equation for this one. Now again, remember that last final step of 2 to the power of n only works because we had the same base, so the 2 times 2 to n minus 1. That's not going to happen very often. So you generally aren't going to be doing any simplifying for these explicit equations, but since we could simplify, we might as well just use our exponent properties and make it a little bit simpler. So that was just something we could do in this one that's kind of fancy, I guess. Okay, so now what we're going to do is we're going to look at some more sequences and find the common ratio, writing a recursive equation, and then explicit, and then finding a fifth term. So let's check it out. All right, so we have two different types here, right? We have one with fractions, and we have another one where we have an exponent. So we're going to be looking at, two different types of math techniques. So we got to definitely make sure we understand both our fraction properties and, for that problem number 2, our exponent properties. All right. So this is kind of, pulling on stuff that you guys have seen in previous units. So let's check out the first one. All right. First, we want to figure out the common ratio. So to do this, we take, like before, we would take the second term and we would subtract the first term to get our common ratio. We're going to do the same thing, but we're going to divide. So for this one, we would do positive 1/9 divided by the first term, which is negative 1/3. All right, and we know when we divide fractions, we flip the second one and multiply, keep the first, flip the second, change the sign, KFC, right? Because we all love some fried chicken. So 1/9, change it to multiplication, and then flip, so we get 3 over 1. All right, this simplifies to -3/9, which is -1/3. All right, so that should be my common ratio. You always want to check, do it one more time just to make sure. All right, so I'm going to do it with so now I have -1 over 27 divided by 1/9. All right, same deal. Keep the first, change the sign, and then flip it. This is -9 over 27, and then 9 goes into 27 3 times. So this is also -1/3, which is R. So I had the same thing both times. All right, so I have my common ratio. So R equals -1/3. All right, be careful when you're doing ones that have negatives in them. All right, if you're changing sign every other term, so look, we start with a negative, and then 1/9 is positive, and then 1/27 is back to negative, that means your common ratio has to be a negative number. That's the only way that you can change signs from one term to the next. If they're all negative, it's a positive number as your common ratio. If they're all positive, it's a positive number. But if you're alternating, that's an indication that you have a negative common ratio. So look out for that. Okay, so we have our common ratio. Now I want to write our recursive equation. So this one's pretty easy. So recursive, we go a sub n equals a n minus 1 times the common ratio of 1/3. And that's it. That's all you have to do. So recursive equations, usually pretty easy to make, just annoying to use. My box sucks. There we go. That's fine. All right, next up we have our explicit equation. So E for explicit. All right, so this is going to be a sub n, and then we take our first term, which is -1/3, and we multiply that by our common ratio to the power of n minus 1. Now, like the example that we did for up here, right? So the 2 times 2 to the n minus 1, we had the same base, so we could combine them. That happens again here, right? We have the same base number, right? The -1/3 and the -1/3. So we could combine them. You don't have to. Like I said, I know I just said this is rare and doesn't usually happen. And then we just ended up having it happen twice. You could combine these if you want to. Sometimes the negative makes it a little bit strange, so you want to be careful. But since they're both negative, then what you could do is you could combine these, right? You could say, so we have the same base number. This would be an exponent of 1. So ultimately, a sub n equals, you have your -1/3 to the n, right? Because when you add 1 and then n minus 1, you get just n. Yeah, so there you have it, right? Oh, and we want to make sure we have parentheses around this. The reason being is because you want it to alternate, right? You want it to alternate signs, positive to negative. If you leave the negative on the outside, then it's not going to work properly, right? So let's just check. So remember, this is, oops, hold on, we're over here. Yeah. So if we want to get our first term of our sequence is -1/3, all right? So n equals 1, right? So if you plug a 1 in for n, you should get -1/3, all right? So if we plug in a 1, we get -1/3, which is correct, all right? But our second term is positive. So when we take -1/3 and we raise it to the power of 2, if the negative were on the outside of the parentheses, then you would end up with just 1/3 squared and then times the negative on the outside. But we want the negative to be part of the problem. So we want that negative in the parentheses because we want a positive 1/9 for our second term. So the parentheses, the negative has to be in the parentheses. So just be careful with that. But yeah, so there's our explicit equation all simplified. All right, so we're done there. So the last thing we have to do for this problem is to find what the fifth term of the sequence. So we want to find a sub 5. All right, so we're plugging in 5 for n. Now again, you could use the unsimplified equation if you wanted to, this bad boy right here. If you didn't want to simplify, but since we did simplify because our bases were the same, -1/3, I'm going to go ahead and use that simplified equation. So I'm just going to take the -1/3 and raise it to the power of 5. All right, so what this does, remember, it takes -1 and raises it to the 5th, and then 3 and raises it to the 5th. So -1 to the 5th is -1. 3 to the 5th, nobody knows. I don't know what that is. 3 to the power of 5, that's 243. So my 5th term of the sequence is -1 over 243. Pretty big number. Yeah, that's it though. All right, so that is our geometric sequence example number 1. All right, so now we're going to do number 2. Same kind of deal going on over here. All right, we're going to start by taking the second term and dividing it by the first term. First, we're going to move my head so that I'm not in the way of the, oops, wrong box. There we go. I'm just going to go over here. Look, I'm like right here. I'm part of the problem. All right. So 10 to the -1 divided by 10 to the -3. All right. So you have two options. So this isn't technically right like a fraction, so we wouldn't really want to flip it. But if you want to do it, write it like this, 10 to the -1 divided by 10 to the -3. Remember, you subtract your exponents when you're dividing. Like if we had this situation, we would subtract our exponents. So we have -1 minus -3, -1 minus -3, that becomes 10 to the second. Yeah, 10 to the second. All right. So this would be our common ratio, right? So we just subtract. So when you're dividing fractions, if they have the same base, you subtract their exponents. All right, so we'll do it again. So 10 to the first divided by 10 to the -1st. All right, so again, these aren't really fractions, so I'm just gonna like put them like division with the sign in the middle instead of doing the flippy thing. You could do the flippy thing, but it's just weird because we have whole numbers, so like why would we want to do that? Anyways, we have 10 to the first divided by 10 to the -1st equals, so we subtract 10, so 1 minus -1 gives us 2, +2. So again, we have the same common ratio. All right, so now we have our common ratio. So R equals 10 to the power of 2. Oops, let's scroll. All right, so next up we want to make our recursive equation, which, remember, these ones are kind of easy. Oops, let's do a little dot dot. All right, a sub n equals, all right, a sub n minus 1 times our common ratio of 10 squared. All right, now you might be thinking, can I just change this to 100? 10 squared is 100. I mean, technically you can, but I mean, you don't really want to. I mean, because our sequence is in exponent form, right? It's like 10 to the -3, -1, blah, blah, blah. We want to keep the sequence in that formatting. So if you change it to 100, then when we're going to find our 5th term, it's not going to be in that kind of the same way our sequence is. And you always want to keep them in the form that you're given. All right, we talked about this with our trig units, right? So if you're given something in radians, you want to keep it in radians. You don't want to convert to degrees and answer the problem that way. The same kind of thing applies here, right? So if we have it in exponential form, we want to keep it in exponential form. So yes, I know that 10 squared is 100. We want to keep it as 10 squared. I hope that makes sense. All right, so this is our recursive equation. All right, so now we need explicit. All right, so a sub n equals, so our first term is 10 to the power of -3 times our common ratio of 10 squared to the power of n minus 1. All right, now we can simplify this. We know some exponent rules. All right, so first off, when you're raising something, an exponent to an exponent, you want to distribute. So we're going to go ahead and distribute that to the part outside. So now we have a sub n equals 10 to the -3 times 10 to the 2n minus 2. All right, so we just distributed. All right, now because we do have the same base, again, even though I told you it was it was rare. It is really not that common. I guess I just picked some problems that had it happen. I don't know what was going on. Anyways, we want to add the base. We want to add our exponents, right? So we're multiplying bases. We want to add our exponents. So we have 2n minus 2, and then we have a minus 3. So we're going to add. That's going to give us a sub n equals 10 to the 2n minus 5. And that is our explicit equation. All right, so last but not least, we want the fifth term. So we want a sub 5. So we're going to plug in 5 for n. So this is 10 to the 10 minus 5, which is just 10 to the 5th. And that's where we want to leave it. We want to use our oops, you guys can't see that because it went sideways. There we go. And remember, we don't want to actually type this into our calculator. Look at our sequence, right? Our sequence has all of the terms like with an exponent. So we want to keep that formatting. So we just want to leave it as 10 to the 5th. That's it. That's our final answer. We don't want to do 10 to the 5th in our calculator and then really it's just tack on 5 zeros. We don't want to do that. All right, 10 to the 5th is our answer, and that is it. That's where we want to stop. So that is our video for today. I hope it was helpful. We'll go over some examples in class together. But yeah, second to last video. That's amazing.